G'day ladies and gentlemen, and welcome to another episode of What's Up Mate. Now, I've been asked by a few listeners to jump over to residential AC systems and specifically how we install, test and commission our systems. Looking at pressures, temperatures and airflows. Now, commissioning for most busy techs is turning it on, waiting for the outdoor unit to fire up and hitting the road onto the next poorly commissioned installation. Now, people reaching out and asking for content is pretty special, especially for such a young podcast with a very limited audience. Now, there will be a lot of people out there listening to this wondering, why do we need to touch up on the basics? Surely everyone knows this stuff. Well, no, not everyone knows this stuff, and there are people out there that know this stuff but refuse to put it into practice, and there is a number of reasons for this. Is it because they are just too busy? You've got too much on your plate? I can relate to that, but still, you should be doing these as a minimum on each install. Is it they are sparkies or plumbers who have only completed a week short course into how to install split systems with very limited, if any, learning on the refrigeration cycle and refrigerants? Or perhaps you're an apprentice early on in their career who haven't quite grasped the concept yet. That's fine. One day you will wake up and it all makes sense, but until it does, you're in the right place to help you gain that foundation of the principles of the trade. Perhaps you're a fully qualified sparky and have made the jump to a dual trade apprenticeship and want to get ahead of the game. Or maybe you're between jobs and you're just sick of listening to commercial radio and want to stretch the brain a little bit. Whatever your reason, remember that any knowledge you gain, you are getting ahead of the competition and helping your clients to a more comfortable, safer and energy efficient environment to live and work in. So step one, before you even start the job, when you or the boss are on site quoting, there are a few things to consider. Heat loading of the space you're looking to condition. Things to take into account are solar loading, so sunlight entering into the building or hitting building surfaces, appliances within the conditioned space, persons occupying the space, infiltration, which basically means how many times a room's air changes with that of outdoor air, design temperature of your indoor space, design temperature of your outdoor air temperature as well. So you really need to start looking at your expected highest and lowest, because that will really start to affect how your system performs in high or low ambient conditions. These are all super important, but this list is not exhaustive. I'm going to run through this a bit more in depth in another episode. Or, of course, there's the trusty old faithful rule of thumb calculations. 140 watts per metre squared for a wall split, or 170 watts per metre squared for ducted. Not very scientific, but for costing estimates, not a bad way to size for a unit. Obviously have a discussion with a bit of a disclaimer to your client that, we'll have to do a correct heat load calculation, and the equipment we've chatted about today may not be exactly what we want to use. So just a bit of a disclaimer there, just to protect yourself and also set your expectations for your client that, it probably will change a little bit. Now, inverter technology in the domestic market has probably made the trade a little bit lazy when it comes to sizing up equipment. Many techs are under the impression that the inverter will match the capacity that is required, so if we oversize it, it will be all good. Well, yes, it will ramp down. However, capital equipment costs and inverter efficiency range is what will also affect overall efficiency of your system. So let's not forget our airflow requirements, which make up a huge part of sizing your equipment. Not enough airflow and you'll never maintain a comfort level. Too much airflow and it will impact user comfort significantly. So on to step two. Discuss with the clients about how they would like the installation to look, such as location of indoor units, number of indoor units, location of the outdoor, taking into account unit clearances and noise issues with neighbours or your client. Outdoor unit mounting options, whether that's ground, wall or roof mounting. If you are going to opt for the roof mounting option, which a lot of domestic guys are doing now just because we're talking terraced townhouses, zero backyard, built gutter to gutter, how do you plan on actually making your roof penetrations watertight for the long term? And have you got suitable and safe access for maintenance of that outdoor unit? It is super important to ensure that this is all priced up, because you don't want to be the next service tech that rocks up to service this equipment with no safe access to the roof unit. Drainage. have a chat with them about drainage. Now, will a gravity drain work for your indoor condensate, or will a pump be necessary? Remembering pumps can be noisy and also a point of failure, and do not forget to wire in that high level cutout. Step 3, equipment selection. Equipment selection is a good way of thinking is if you wouldn't install that brand in your own home or that equipment in your own home to solve this issue, don't endorse it to your clients. You've got to have faith in what you're installing. So if you won't install it in your place or your grandma's place, please don't install it in your client's place. Now, we understand that there are a lot of instances where pricing will win the job. So a cheaper unit is obviously going to be the preferred option, but have a chat to the client about reliability, efficiency, after-sale support, and spare parts availability. We all know systems fail when it's a week of 38, 39, 40 degrees in a row. Right. Ask the question if they have a specific brand in mind. Now, for some reason, it always seems to be Daikin or Fujitsu all the way. You might not have great access to these brands through your purchasing network. However, there are always ways to source these to meet your client's wishes. Otherwise, educate them on the reasons why you install your brand. It might be you're the dealers, you're the service techs, you've been installing them for years, you've installed umpteen units, and you've had no dramas. Perfect examples as to why it's probably a good idea maybe for them to listen to your advice. Again, you're the professional. So if you are going to use a brand of unit that is not what you normally install, just make sure you read up on the specific installation manuals for the models before you start any quoting or first fix, etc. You can get stung pretty badly with discrepancies in pipe size between brands for certain capacities. Interconnecting cable, for example, like Daikin's, they're after extra conductors to their indoors. Some are after just a single twin and earth and a single for their interconnect. Some are after a twin and earth and then a shielded two pair or single pair. Sorry. Now, you don't want to look like a dick when you turn around and you're on site ready for second fix and all of a sudden you've got to start running new pipes or new cables. It's just not very professional. So just take that 5 minutes to have a read of the installation manual, look at wiring diagrams, pipe sizes, schematics, whatever you need to make sure that you can get this first fix completed properly. It's, really important. Step 4, congratulations, you've won the job. You arrive on site, now it's time to get this install done and done to a standard you would happily put your sticker on. Now, we just want to confirm with the client the locations and their expectations of the install, and then you're all sweet to get stuck in. Now, you all have installed a splitter or a ducted, so I'm not going to go into the detail on mounting, etc., but make sure it's level as well as adequately supported. They're probably the two main things. Step 5, pipe runs. Now, every manufacturer will specify minimum pipe lengths as well as maximum, but we've all seen installs where the split tails are welded to a short stub of copper and flared straight to the outdoor unit. Now, manufacturers have a few reasons for this minimum pipe run, and a few of these reasons are refrigerant flow noise. You don't want to hear that refrigerant flow, especially when you're changing modes from cooling to heating or vice versa. In auto mode, if that's how the client prefers to use it, it might change 3 or 4 times in a day. You also don't want to hear when the valves open up and you get that inrush of refrigerant, etc. Vibration elimination from a outdoor unit to the indoor unit. Any length beneath what the manufacturers specify is risking having a little bit of noise vibration come through those pipes and get sent through the house. Super annoying, and guess what, there's not really much you can do about it if you don't have a long enough pipe run. Third one, helping to prevent liquid flood back by ensuring there is suitable total system superheat during cooling operation. This is generally only an issue when airflow is an issue across the coil. Basically, you're exposing your pipework to ambient temperatures, so you are going to start boring off that any liquid that is stuck in that suction line on cooling. You're just going to start to heat that up, boil it off, so then it becomes superheated. So then you're getting just a vapor back to your outdoor unit. In heating mode, it's important as well to have the correct pipe run, because you just want to prevent that superheated vapor returning to your outdoor. You want that to de-superheat, so basically starting to come back to more of a closer to an ambient temperature. So as soon as that superheated vapor is turned into, or it does evaporate, condense into your subcooled liquid, that's what we're aiming for. If you have a short pipe run and you've got airflow issues, you'll be starting to slam just basically vapor back to that expansion valve in the outdoor. You're not going to get very efficient expansion back to a low pressure, so you're really going to start losing that heat removal efficiency in your refrigeration system there. So again, pipe length can help with this. Probably more important for your customer will be maintaining a warranty period. Now this is the one that the client is going to be concerned about the most in the middle of summer, when a warranty tech comes out and they do not stand by their warranty because you haven't installed their system to their conditions. Guess who's coming after you with the repair bill? The client. Right, step 6. You've run your pipes. Now it's time to make some connections. Now, making flares. Now, I'm only going to touch in making flares because I think there's a lot to be said about the proper way of welding connections to larger systems or refrigeration systems. We'll touch base with that a bit later. Making flares. Now, we've all made really good flares. We've all made really shit flares. And we've all forgotten to put the flare nut on the pipe before you make the flare. So tips to a good flare: make sure your pipe you're cutting is straight for hard drawn copper. It's no drama. It comes out the factory straight. Your tube cutters go straight on the pipe straight. Everything works sweet. For pair coils is when it becomes a bit of an issue. Make sure you've rolled the pipe out and it is straight as it can be before you make the cut. You don't want your pipe work to be cut on an angle because it's going to affect how your flare is made. You also want to make sure you're actually cutting with an appropriate tube cutter. We're not plumbers, so we're not using a hacksaw or a grinder to cut through anything, because any of that swarf that will find its way into the pipework is going to contaminate the system, block up expansion devices, etc. So really important to use tube cutters and not a hacksaw, etc. for this stuff. Deburring. So once you've made your cut, make sure you deburr the internal of the pipe with a deburring tool. There are a few options out there for this, like the tooling wise. I prefer the pen type blade deburring tool, which just looks like a little big pen with a curved blade at the end. Others are the inside outside deburring tool, which is basically a round cylinder with a blade or rough surface on a cone within that cylinder. These are pretty handy when you're actually using the press style fittings like your B-press or your rapid locking, etc. Because you want to make sure that there's no sharp bits on the external of your pipe as well as your internal. We'll touch more into those sorts of connections type in another episode. Yes, they've got their place. Are they as good as soldering? Who knows? It's really probably personal preference. We use a bit of combination depending on the application. In my experience, soldering and expanding is just probably a little bit quicker. But yeah, there is benefits for using a press type connection. If you don't deburr your system, you deburr your flare before making a flare, you will eventually get a leak, or you'll get a leak straight away. No doubt about it. Doesn't matter how tight you do your flares up, if you go over torque, etc. If you haven't deburred and you've got a pour edge on your flare, you will get a leak. If you're working on soft drawn copper, so pair coil, you're good to get flaring basically straight away. If you're working on hard drawn, you'll need to anneal the copper, so heat it up to cherry red, let it cool. If you don't do this, you're basically going to crack the pipe. You want to make sure you let it cool before touching it and flaring it. Obviously, you'll get burnt hands. Now, you've heated the pipe. You're going to get a bit of carbon build up in that pipe work. Really important to also make sure any of that carbon build up is removed before you connect it to the system. Best case, like you're doing everything perfect, you're actually purging some nitrogen through that while you're heating it up to cherry red. Again, the likelihood of somebody doing this to do one flare is pretty minimal. So just please make sure you get rid of all that build up, etc. So super important. Get rid of any of that carbon build up. Right. Slide your flare nut on and get your flare tool ready. You're good to go. Make sure you align your flare block so that the copper protrudes by about the wall thickness of the tube you're working on, or up to about the thickness of a 5 cent piece, depending on how big a flare you're making. The bigger the flare, the more you're going to need extending over the top of that flare block. There's so many different style of flare blocks now. I use a ratcheting type flare block, which is brilliant for tight locations as well, because you don't need to fully rotate that flare handle. You can literally just ratchet it in small little portions if need be. There's the old style full turn flare block, which are the cheapest, and now there's even drill attachments you can use. I haven't personally used them. There's also actually battery operated flare blocks now with a depth gauge, so you're going to get a perfect flare every time. Again, I haven't used one of these. I've seen them in suppliers, pretty interested by them, but yeah, still haven't used anything like that. However you do your flares, it is important to make sure your tool is lubricated. I use the same oil I put on my flare connections, as well as ensure before each install I put a bit of the same oil onto the face of the flare tool so that the tool is lubricated against the surface of the copper. This saves contamination with different oil types, but also makes for a nice smooth flare. Cool. So step 7, connecting the pipework to the units, indoor and outdoor. You've met your minimum length, sweet. You're under the maximum length, sweet. You might have to record how much pipework you've gone above and over the pre-charge length, but that's easy to do. We're not worried about that right now. Now's the time to join your pipes. Again, all your joins. Why do we do this? Well, it's pretty simple. Less friction. You won't deform your flare or twist your pipework as you're tightening it up. Now, oil needs to be put on the rear of the flare and also the face of the flare. This is why we use refrigerant oil, and I also put oil in the thread of the fitting. So we've got 3 spots there for oil. So at the rear of the flare, between the flare and the flare nut, the face of the flare which presses onto the brass fitting, and then also just the thread on the male thread of the flare connection. Again, it's just all about friction and making sure that nothing is going to compress that copper or twist it or break it. So we've done that. Now torquing your connections. I'm not meaning like let's just have a chat. I mean actually torquing your connections up to a specific torque value to prevent leaks. Now the manufacturer is going to specify the torque settings, which will vary from size to size for your copper. So too tight and you risk crushing your flare and breaking the mechanical seal, cracking the flare nut straight away or over time as the brass expands and contracts with the temperature change in heating and cooling modes. Too loose, obviously it's going to leak. We're working with pretty high pressures, guys, so we've got to find that really happy medium. The easiest way to do that is just follow the manufacturer's specs. Now, it's funny, I remember back to when I was an apprentice, I had a tradie I learned a bit from, and he had a pretty big motto that he went, big pipe, big spanner, little pipe, little spanner. Now, I was pretty young and naive back then, and it did make sense. I wasn't aware of of the torque values, etc. But yeah, I'm not sure how many callbacks he's got from refrigerant leaks over his years, but this is definitely not the best practice, but unfortunately it is pretty common out there. Step 8, nitrogen pressure testing. A lot of people don't do it, and fair enough. It does take a little bit of time, but it is the only real way to be 100% sure you've made decent flares. It also, to be honest, really helps when you're evacuating your system too. Now, whenever we pressure test, we want to pull a vacuum really quickly before we do a pressure test, just to remove the air from the system before we put the dry nitrogen in. This minimizes the temperature/pressure fluctuation with air in the system. How much pressure? Everyone's got their own way of doing this, but every piece of equipment will have a maximum and minimum pressure rating. This is important to get your head around in the refrigeration industry, especially where evaporators are designed and manufactured with lower operating temperature, therefore lower pressures, and manufacturers are finding cheaper ways to manufacture their goods. If they can get away with it, they're going to start using thinner wall thicknesses, etc. So yeah, just be really mindful that you do actually check your low side on your refrigeration systems much better. Like, look at your maximum pressure that's able to be pressure tested to. But in reverse cycle air conditioning, generally speaking, they're going to be running on heating and cooling, so we're exposing them to lower pressures. But also on heating mode, we got high pressure, so we're normally pretty sweet. So I always aim for 3000 kPa for an hour. Now, when we pressure test, I actually use our Testo digital manifolds, as the resolution is so much better. So you're actually going to pick up a microscopic leak, maybe not microscopic, but you will pick up a small leak a lot faster than you would on a analog manifold. Again, it's just handy. You know straight away you've got a leak. You're not waiting an hour and then going, oh, there could be a leak here. There's another fact that why we use the Testo manifolds is that they've actually got a built-in pressure temperature compensation. Although nitrogen is quite stable, the pressure will still fluctuate depending on the temperature. We use it because it's inert. Yes, it doesn't react a lot with temperature, but it still does. So if your ambient temperature drops, it might look like you've got a leak if you don't use the pressure temperature compensation. Or if the temperature rises, your pressure rises, and you're going, what the hell? Like, it is important to make sure that if it's pressure testing, you understand how and why you're pressure testing and how temperature is going to affect that. If you've got a tool that can help you calculate that so you know you're bang on, use it. So simple, so easy. Step 9, now evacuation. Now, I cannot imagine, I can't even put a number to the amount of videos or discussions I've looked at or seen, or even chats at trade school or with apprentices, etc., about the different opinions on the best way how to evacuate your system. Now, some are heaps better than others, some are faster than others, some are the right way to doing it, in my opinion, some are not. But there's a million different ways. I'm going to discuss the ways that we see out there in the field. I'm also going to discuss probably the best way, which is the way that we do it, and that's also incorporating what we call a decay test, which is pretty handy. It'll prove if you've got a small leak. It'll also prove if you've still got moisture in your system after your evacuation down to your specified micron value. So why do we want to pull a vacuum? There's a few reasons. Air contains moisture, which is non-condensable, which is going to affect your system performance. The moisture, if left in the system, will affect your oil and turn it acidic, which is no good for your windings of your compressor motor. If you don't evacuate correctly, you will have premature failure of your compressor due to burnt out windings or insulation breakdown of those windings, which isn't a good thing. As we all know, compressor changes can be expensive, and you're not just swapping the compressor, you're often reclaiming all the refrigerant, getting rid of that, putting fresh refrigerant in, putting burnout dryers, all sorts of stuff in. Really, really important to do all this stuff. So let's make sure we evacuate it correctly so this does not become an issue. There's also other ways to prevent moisture ingressing into a system. In refrigeration, that's HPLP switches, safety controls, all sorts of stuff. We won't go into that today. So there's a few techs out there who will always evacuate through a manifold and have their vac stat on their pump. Now, a few points for at least having a vac stat, I guess, but you're only reading the vacuum achieved at the pump and not in your system. Now, this is important if you want to test your pump is operating, but you cannot rely upon this reading to prove that you've got a a decent micron reading or vac reading in your system, because your vac stat's too far away from your system. Now, there's also the 2 smokes and a coffee method. I'll let you use your imagination, but can almost guarantee they have not even achieved any vacuum requirements. There's also it's below atmospheric on my gauge, we're all good method. Again, how do you know that you've pulled the moisture out? Yeah, it's easy to pull a vacuum and get something below atmospheric pressure. You could probably do that through a straw, but you don't have a decent micron reading. Again, terrible method. There's the method where they're using a vac stat, but they've installed it on the manifold. So you're reading, so from your vac pump through to your yellow hose to your common port on your manifold, and then your vac stat's basically sitting on top of your yellow hose, reading from there, then off to your suction or your liquid or both, depending on where your port is on your equipment you're evacuating. Again, probably better than the first method I mentioned with the vac stat being on the pump, because you're obviously a little bit closer to the system. Again, you're not reading a true system evacuation. So there's the T-piece at the access valve and a vac stat there. Now we're getting somewhere, or at least you're getting close to reading your system evacuation, but you've still connected your manifold to do this. Not a problem using a manifold, don't get me wrong. It's just another restriction, and it's also a potential leak point for your vac, so you're not going to do it really fast. You may actually be pulling air back through that, through like loose or poor rubbers or poor nylon seals on your gauge, on your hose lines if they haven't been maintained correctly or stored correctly. Also, the rubber hoses that are on your manifolds are generally not vacuum rated, so they will actually bypass a little bit. Not a heap. Like, if you want to get super anal about it, it'll work, yes. Is it the best method? Probably not. So you've got a T, so you've actually got your vac stat basically right on where you're accessing your system. Pretty decent, like you've done a really good job. You're reading as close to the system as you can, as far away from your vac pump as possible, but you could still do a little bit better. You need to do a decay test. Now, our method is basically this, and it's, if you want to see a video of how we do it, on our Instagram page, Sparrow Electrical, you'll actually see our recent install. We've actually shown it. There's been a few images we've chucked up where we haven't used a method. We're just always trying to better ourselves as techs. So our method at the moment is we're using a vacuum rated hose straight from the pump to a core removal tool with a T-piece and a valve, basically all in one fitting. So we've only really got 3 connections, so one at the pump, one from the hose to the removal tool, and then from the removal tool to the system. So three connections, so 3 potential leak points. There's a valve removal tool, so we're actually removing the valve out of the system, because again, a valve is a restriction. It's just going to slow down that evacuation process, which we all know sometimes you're in a rush and you still want to make sure you pull a good vac, but you just can't not do it if you've got restrictions. It just takes time. So we actually remove that. So we actually still got pressure in our system still. So we're actually going to release all the nitrogen from the system to just above atmospheric pressure, around that 10 kPa mark. Remove our hoses. Basically, this ensures our system is at a slight positive pressure when disconnecting and reconnecting, just so we're not bringing any moisture in from atmosphere via the service port. We've got a positive pressure, so the nitrogen is going to want to push out before anything comes in. We're going to connect. We use the Appian valve removing tools. They're just super compact, super easy to use. We remove the Schroeder valve out and turn the valve tool to the closed position. So you will get a little bit of nitrogen released. Again, you're not going to lose all of it. There'll still be a small amount of nitrogen there, so you've got a slight positive pressure. At this point, we want to connect our vac stat to the port on our valve removal tool. Now, on the Appian tools, where the vac stat connects, there's actually a Schroeder valve on there, so you'll get a little bit of nitrogen coming out when you connect that up, but it's not open to atmosphere, so to speak. We're going to connect our vacuum rated hose then to the removal tool and pump. We're going to open up the 1/4-inch port on the pump and start the pump. This is just a way to prevent the startup current on your pump skyrocketing. Great for the battery pumps or ensuring longevity of your equipment if you're just using a 240 volt pump, because you're not straight away pulling that into a vacuum. Like, it's just a soft start way basically of getting your pump up to speed and then putting a bit of load on it. So we close that 1/4-inch fitting on the pump, and then we open up the valve on the valve removal tool. So now we're sucking directly from the pump through our vacuum rated hose, which is quite a large diameter hose, straight through the valve where the core has been removed, and we're basically just pulling straight through the suction line, which again is a big pipe through to the evaporator or to the indoor coil, and away you go. So depending on system size, I'd expect to achieve under 500 microns within a few minutes with this method, which is pretty good. Now 500 microns is the minimum requirement. However, there's a few manufacturers specifying below 400 now. So just make sure the equipment you're installing, you've actually checked to see. Again, it's all about moisture and acidity in the compressors. So for this example, let's just pull our vacuum to 250 microns. And this is now we're getting ready for what's called the decay test or the positive pressure test. Close the valve on your core removal tool and then turn your pump off. So you've isolated the system from your pump before you've turned your pump off. If you don't and you turn your pump off and then isolate the system, you're actually going to bring in a fair bit of external, or maybe even suck some oil back from your vac pump up your line and into your line set, which is a problem. You're gonna have to sort that problem out. You've brought in dirty vac pump oil, so you're not really good for a brand new system, let's be honest. Right, now we've done this, we want to make sure that our micron or our vac stat, whatever you want to call it, is staying steady at that level that we've removed the vac pump from and closed the valve. Now, roughly over half an hour should be enough for this test. That's all we do. And ensure that your gauge doesn't increase its micron rating. So let's say we've stopped it at 250 and it stays at 250 for half an hour. You're sweet. You don't have any sign of moisture remaining in the system. You don't have any sign of a small leak. You're good to go. If it's a minor increase, like you might go from 250 to 300, like that's 50 microns over half an hour. There is a specific value. I'll dig that up and check it out. That just to me identifies you've either got a very small leak or, which to be honest, you're probably not going to find it, that's very small, or you've got a bit of moisture in your system. So it might be time to think about maybe doing a triple vac or just running that vac pump for a little bit longer until you do get that constant 250 or whatever you set your vac pump to before you do your decay test. If you've got a major increase, so let's say you go from 250 microns over 2,000 microns in the space of a few minutes, you've probably got a leak somewhere. You might have just forgotten to do up one of your flares tight enough. Maybe one of your to be honest, I've done this where I've not completed a weld properly. I didn't actually do a pressure test, but I did a decay test, and I noticed straight away my microns were just going through the roof. Then I was like, I better do a pressure test, and then I found just on the back of a 3/4 weld, it had leaked, and I didn't pick it up, and that's because I didn't do the pressure test. If I did the pressure test, I wouldn't have had to do things twice. So it's generally not a problem for systems that you've just installed, but you might have some big issues maintaining a vacuum for an extended period of time on a system that's been running for a period of time, or you are trying to evacuate like the full condensing unit, compressor, evaporator. We're going to just dive into that a little bit later on. Like, it's a pretty in-depth conversation, that one, which I'll actually have a chat. We'll bring another Friggy on just to have that chat, I reckon, just because it does go so in-depth. But cool, so we're happy with our decay test on this new splitter we've just installed. We want to put the core back in, obviously, because as soon as you take your gauges off, guess what's going to, or your hose is off and you open that valve, what's going to happen? You're just going to undo all that hard work you've done and bring a heap of moisture back into the system, and you're back to the start again. So easiest way, best way to do this, open the service valve and allow the refrigerant within the system to increase just above atmospheric pressure. So you don't want to put too much into the system with your vac stat still connected so that you damage that. You also don't want to suck in air when you're reinstalling the valve core. So it's a little bit of a balancing act here, guys. But once the valve core has been reinstalled with the positive pressure behind it, you can remove and pack away all your vac tools. Your job done. That's all sorted. Step 10, we're going to release the refrigerant into the system. Like, we're nearly done. Like, super easy. We just want to slowly open both service valves until pressure equalizes, like to just like a couple of like probably not even 3/4 of a turn, maybe half a turn anti-clockwise. Let that refrigerant slowly release into that pipework and to that indoor unit. We don't want to do it quickly, so best practice for this is just back them both off slightly. You'll hear that it will slowly release the refrigerant out into the system. Pressures are equalised, then you're good to go. You can just fully backseat them as fast as you like. Then the reason we want to do this slowly is basically we want to retain the oil that's in that compressor in the compressor. We just do not want that high velocity refrigerant flowing out of the outdoor unit into the indoor unit, bringing that compressor oil with it. Obviously it's pretty good for it to be in the compressor. Pretty important. Right. Now, you're pretty well good to go, right? Like, you've pressure tested, sweet. You've installed all the equipment properly, sweet. Either you or a Sparky, or you might be dual trade, so you've done the electrical supply, tested all that, sweet. You could just turn it on and leave, right? Well, yeah, in a way, yeah. You still need to test the equipment on both modes, both heating and cooling, and ensure that your pressure, temperatures, and drains are working. Now, drains are pretty important, especially more so if you've got a trap. You want to make sure that you've actually primed the trap on a ducted system if you've got a trap on a negative pressure drain, just because otherwise, guess what? The static pressure of that system will basically bring air up through the drain and hold that water back, and you'll flood the roof space. You also just want to make sure that your drains are flowing freely, so both for splitties and for ductors. Just make sure that, you know, when you pour water in the indoor unit, that it does actually come out the drain, you know, with decent fall, etc. So you've done all that, you've tested your drains. Now we're good to turn the system on and just check it out in both modes. Some systems, specifically like some of the Mitsubishi Heavies we've found, or also the Dakins, will actually run into a test mode. Again, you might be scratching your head, it'll actually start running on cooling, even though you've asked it to run on heating. Just have a quick read of that startup procedure. It's pretty important, and it might save an embarrassing phone call to tech support. Some systems, on the other hand, won't actually operate unless the crankcase heater has been energised for more than 24 hours. Now, this is probably more on your commercial, larger systems, VRF, package units, etc. Again, it's just a way of, they're part of the manufacturer's startup procedure, which should be followed. You can bypass it, wouldn't recommend. Right. Some manufacturers recommend the crankcase heaters actually operate for even 10 minutes before the system startup. Every manufacturer is going to be different. The sole purpose of the crankcase heater is to prevent refrigerant migration, basically liquid refrigerant finding its way to the coldest point into the compressor and mixing with the oil in the system whilst the system is off. Now, I've done about 3 condensing unit changeovers in the last couple of weeks throughout Adelaide, and on each of them I've actually found that the crankcase heaters were wired on all the time. You don't want your crankcase heater while your compressor is running. It's frustrating. It's really easy. Like, the normally closed contact on your compressor start contactor is going to be a friend for this scenario. Just wire it through the normally closed. So normally closed means that those contacts are closed when the coil's not energized. So when the compressor's not running, the coils are closed. As soon as the compressor starts, those coils open and your crankcase heater will stop operation. Really simple, guys. In Australia, we're actually really lucky. The refrigerants that we use, especially in air conditioning, are basically the temperature that they are in a liquid form is well below our average lowest temperatures, even in like the alpine regions of Victoria, New South Wales, Tasmania even. Like, that's a pretty cold place, but you know, we're always pretty sweet. So domestic AC are pretty sweet to start up straight away without the crankcase heaters being on. However, commercial equipment with multiple compressors, oil return systems, etc., I would always allow the crankcase heaters to run as specified before startup procedure each and every time. Again, it's a warranty thing, oil return thing, super important. A little trick for unit startup is, if it's wintertime, test your heating mode first, so then, you know, it's easy. The indoor unit will want to run into cooling mode, and vice versa. If it's the middle of summer, just check your cooling mode first and then check for your heating mode. It's really easy. You want to check running pressures and temperatures on both. Now, I've actually done a video on this just for a wall split. If you're interested in looking at it, on our Sparrow Electrical Instagram page, have a look. It's very basic. I'm going to go into a bit more detail on a refrigeration system, watching both the high side and the low side pressures with a refrigeration system on a startup. Cool. Heating. It's heating season in Australia right now. Like, it's autumn, it's getting chilly. We've been installing multiple systems for heating at the moment. It's super easy to commission a system when your ambients are either really cold or for heating, or really hot for cooling. It's always super tricky in that in between, sort of the fringe, which is sort of what we're getting when we're finishing our installs. Like, it might be 20, 22, but the nighttime temperatures might be getting down to 5. So again, if you are adding refrigerant or you're doing a repair, I would recommend highly to making sure that your ambient temperatures are at an extreme. You just get better test results and confirm that it's working. On a cooling only system, you might just be struggling for ambient temperature days to do it. Again, to mimic a high ambient temperature, get a bit of cardboard and just block that outdoor coil up a little bit, so then your discharge temperature off your air off of the fan coil is up around what you would expect to see, like 15k above a high ambient day. Like, let's say it's 35 degrees, 15k above that, 50 degrees air off of that coil would be ideal, is what we're looking for. Again, that's going to raise your head pressure and sort of mimic that, and making sure then your subcooling, etc., on your coils, you're pretty sweet. And then your superheat, etc., inside, hard to mimic a warm house, but yeah, it'll get you close to a decent commission. Now, inverter-driven compressors, are a bit of a pain to ensure pressures are correct, as they will fluctuate depending on the demand of heating and cooling required. But if we're testing on heating, we want to make sure our condensation temperature pressure is at least 15 degrees above our indoor temperature for efficient heat transfer. Basically, the higher the temperature difference above 15, the more heat transfer. Now, if it's super cold inside the space you're heating, expect your pressures to slowly climb as the room temperature increases, whilst maintaining a stable subcooling value. Now, an inverter will generally modulate the speed of the compressor to maintain a stable suction pressure, which will equate to about 5 degrees Celsius on cooling mode, depending, obviously your pressure then will dependent on the refrigerant you're using. So if it's R22, not many inverter-driven R22 systems out there anymore. 410A, R32 are probably the two most common ones you're going to see now on newer equipment. So you generally cannot guarantee a decent charge if you're just looking at that. Again, we need to make sure we've checked a few other things before we go, it's the refrigerant charge. So it might look like it's cooling, but it's not. Again, you're going to have to start to use a few extra tools here. Fixed speed equipment, on the other hand, is really easy to check if you've got an issue with a charge. Basically, you're going to be running a really low suction temperature if you've got a poorly charged, like an undercharged system. Again, if you've got an overcharged system, expect your suction temperature or your head pressure, so your high pressure side, to be higher than expected. Really easy to work on the fixed speed stuff. Sometimes you might get lucky, you might actually get an inverter that actually has a display on the outdoor unit, which will actually tell you what capacity that compressor is running at. Now, whether that's a percentage, like 100% of its nominal, 110%, because they will ramp up a little bit faster than if need be, to maintain a stable back pressure. It might even just give you a value of hertz, like 50 hertz is, 50 hertz is what we work with in Australia. So 50 hertz is actually 100%. 60 would be above, and then it will ramp up and down depending on the loading and pressures, etc. The compressor's reading. If your values, like if you're not certain on the charge and your pressures and temperatures, subcooling, superheat values are all around the industry benchmark, your system is likely charged correctly. But if you're still having issues around client comfort, perhaps it's an airflow issue, perhaps it's a capacity issue, right? If your values are away from industry benchmarks and you have clean filters, good airflows, and you're just not seeing the results of your equipment, it's possible that the outdoor ambient is too extreme and it's limiting the capacity of your equipment. some fixes to this are ensuring airflow over your outdoor coil is adequate and suitable for the application, so not too much, not too much airflow, and not too little airflow as well. Perhaps your outdoor unit is on a northern or western wall, it's just copping that afternoon sun. Maybe chuck some shade cloth over the area to reduce that ambient temperature. Perhaps you discharge air off your coil is just hitting the fan, just short cycling back to your outdoor. Maybe you'll have to look at raising that unit up for your client. Again, in cooler weather, cool air like sinks, if you've got it in an enclosed space, you're just going to freeze that outdoor unit. It will end up in defrost a fair bit of the time. There's a huge long list of external factors that are going to reduce the capacity of equipment. Again, it comes down to design and locations of your equipment to get the best out of your equipment. So if you've ruled it all out and you're still unsure if your system is operating at its potential, psychrometric charts will be your friend. Psychrometrics. Psychrometric. So this is basically how you plot your temperatures and capacities on a chart. And you're going to identify pretty quickly if your system is running at a capacity. Really easy to do this on a fixed speed. Inverter compressors are a little bit more difficult. You really want to make sure that you've got that inverter ramping up at 100%. If you don't, you just take it with a grain of salt, your final capacity off your psychrometric charts. This has just been again, a little bit tricky. If you've got the right tooling, it's really easy to plot it. There's heaps of good apps out there now for plotting against psychrometric charts, and then you just confirm your airflow with a flow hood, how much airflow you're getting over your coils, confirm that with a manufacturer's spec, and just do a comparison. Like, this is the airflow I've got from my manufacturer's spec, this is the airflow that I've got from like in real life. Yes, it's the same. These are the values I'm getting at this data range on this setting for my equipment. That's what I'm measuring in the field. I'm plotting that onto a psychrometric chart. Let's say you've got a 14 kilowatt ducted, you've got and you're within its operating range, etc. You've got the right airflows, your airflows are matching up, everything's all sweet there, but your final calculation comes in at like 10 kilowatts. You've got an issue there with probably being undercharged, overcharged. Maybe you've got some leaky ductwork. Maybe your ductwork's not suitable for the climate zone it's been installed in. More on that a bit later on. Perhaps your insulation on your suction line's not quite there and it's not adequate enough. You're running through high ambience on top of a roof. There's all sorts of things that are going to reduce your capacity in your system. Another really easy trick to see if you have a correctly charged system is, like with any sort of equipment, is just to see if you've got condensation forming on your suction line at your compressor. Again, not very scientific, but it's a pretty good rule of thumb. If you've got a sweaty suction line at your compressor, you've got a pretty much a bang-on charge. This is a really good way of doing critical charge systems, so you're not attaching valves, etc., pressure monitors to your, or transducers, whatever you want to call it, to your system, letting little bits of refrigerant in and out each time you do that. So just that sweating back is a pretty good, like, first visual inspection you can do generally. If you've got ice on any residential indoor unit or commercial indoor unit, you've got an issue, probably either a airflow issue, dirty coil, etc. It is an issue. Rectify that one pretty quick, smart. Cool. That's a very, very quick, super quick skim over the top of just the basics, how we do a few things. I've done a video again over on a Sparrow Electrical Instagram page which goes into the pressures that you would expect on a split inverter system on startup. So really good benchmark. Maybe you guys could just write a few notes and just check that every time you're out there doing some service work. Just compare that with something that's just been installed, you know, even do it yourself. Check it out next time you do one. So hopefully you guys have remembered some things you may have been taught at trade school that you've maybe not put into practice out in the tools, or perhaps you've learned something that your tradesperson hasn't quite taught you yet or isn't even doing. So thanks for listening, guys and girls. That's just another episode of What's Up, Mate, a podcast by an Australian tech for an Australian tech.